In this video, we will discuss about electric flux density. We know the electric field is represented by as E, right? And it is a vector. And now we will introduce another quantity which is known as the electric flux density. Okay, electric flux density is given as it is denoted as D, and D is given as the epsilon naught into D, okay, into E, sorry, epsilon naught into E. So you know that E is usually a function of epsilon or epsilon naught or epsilon, okay, in general. So you can now define a new quantity, electric flux density, D as epsilon naught into E. That means this is independent of the epsilon naught, or we can say in general epsilon, okay. So we know that suppose due to a point charge Q, the electric field at a distance r, or let's say this is r is the vector. So the electric field at this point E is given as 1 by 4 pi epsilon 0, then Q divided by Q into the vector r divided by the magnitude of vector r whole cube. But D is given as epsilon naught into E, which is equal to 1 by 4 pi. If I multiply with epsilon naught, then the numerator, the epsilon naught in the numerator and the denominator will cancel. Then I will get 1 by 4 pi into Q into r bar divided by the magnitude of r bar the whole cube. And the unit for D is given as coulombs per square meter or meter square, or in general we will say as coulombs per meter square. So I hope this is clear to you. Thank you. So next we will discuss about the Gauss's law. The Gauss's law states that the total electric flux through any closed surface is equal to the total charge enclosed by that surface, okay. So before that, we will first define what is electric flux. So what is electric flux? So electric flux. So you know that we have already defined what is electric flux density, which is D. So electric flux density, you know, electric flux density is given as D, okay. Now we will define what is electric flux. Let us assume that the electric field is, let us consider some electric field like this, and let us consider a surface which is orthogonal to that electric field. You can see here I have kept a surface, some surface here. So electric field will be penetrating through this surface. This is an imaginary surface, you can say. So this is electric field, or I can say this is electric flux density D, which is passing through the surface. And you know that in general we define the normal to the surface like in this direction. So this will be the direction of the normal, or it is the direction of the normal to the surface, or I can say it is the direction of this ds. So I can say that my ds, I can define like ds is having some magnitude and the direction is the normal, okay. Now you see here that whatever be the flux, all will be penetrating through this surface, okay. So this is the surface. Now let us consider another case. I keep a surface like this, okay, and the electric field is coming from here, or electric flux density, let's say D. So electric field is coming through this. Now the normal to the surface, I can define the normal to the surface like this. This is my normal to the surface. Now you see here that the normal to the surface and the D So D and AN are perpendicular. So in the previous case, D and the normal to the surface are parallel. Okay. So this is the difference. Now if it is parallel, you see here that all the flux will be going through this surface. Now let us define, now here you see here that in this case you can see here that no flux will be passing through the surface, it will not be penetrating through the surface. So I can define something known as D dot ds. So this term will give you how much electric flux is going through a small area which is ds. Okay. So ds is a small area, you can consider here ds. Okay. So the direction of the ds in this two cases both are different. You see here the direction of the normal is now here it is parallel, and in the previous and in this case it is perpendicular, and here no flux will be penetrating through the surface. So I can define this with the dot product, because the dot product will give you zero effect when the two quantities are orthogonal, and it will give you the maximum effect when they are parallel. So it is better to define with D dot ds. So how much is the flux which is penetrating through this surface? So D is the flux density, that means it is the flux per unit area. This is the flux per area, or I can say that the unit is coulomb per meter square. The unit of flux is coulomb, that we will see later why it is so. So D dot ds will give you how much flux is penetrating through your area. Now if I do the integration, then I can find what is the total effect. So if I am finding the integration over the whole surface, let us say the surface is given as S. So if I am integrating over the whole surface, I will get the total flux. So this is known as the I will get the total flux psi through this surface, through the surface S. Okay. So you see here that the psi is having, actually this is the total flux, psi is the total flux and D is the flux density. If you multiply with the area, then you will get the flux through the small area ds. Then if you are integrating, you will be getting the total flux. So this is the definition for the flux through an area. Now we will see what the Gauss's law states. Gauss's law states that the total electric flux through any closed surface, that is a closed surface, it should be a closed surface first. Let us assume that we have some charge here. Now let us consider some closed surface around this charge. Okay. Now this is a sphere, let us say this is a sphere or the spherical surface, and the area is, let us say, ds. So you know that the normal will be like this, an. Okay. Then the electric field lines you can expect like this, electric field lines, and corresponding electric flux density, let us say d is the flux density. Okay. Now what will be that d dot ds? You see here d dot ds. Okay. So d dot ds. So what is d dot ds? Now the direction of the d dot ds will be the magnitude of d into magnitude of ds. So this will be the small flux through that area. So d phi is the small flux through that area, which is given as the magnitude of d into magnitude of ds and into the cosine of angle between them. What is the cosine of angle between them? Suppose there is a flux, suppose let us consider this flux which is coming through this. Now you see that the angle between them is, you see here, the angle between D and AN is 0 degrees. Okay. So this will be cosine of 0, which is equal to 1. Now our d phi, I will get it as the magnitude of d into the magnitude of ds. Okay. So what will be that? So you see here, this is d phi. So let us consider d phi, d psi, sorry, not phi, psi, d psi is equal to the magnitude of d. What is d? D is nothing but epsilon naught into E, right? Now we will take the magnitude, because d is equal to epsilon naught into E. So then into magnitude of ds. Now you see here that this will be, what will be the electric field at this point? Let's say the distance is r. So the magnitude of the electric field, or the magnitude of epsilon naught into electric field. So epsilon naught into electric field, you will get it as 1 by 4 pi. Okay. Epsilon naught into E, that will cancel. So epsilon naught will not be there in this term. So 1 by 4 pi into Q divided by the magnitude of, that means the distance, that distance is r square. Okay. So distance is r, so we will be having r square. That is the equation for the electric field. Okay. Because there is no direction here now. So into magnitude of ds. So this will be my d psi. Okay, d psi. Now if I want to find the total flux, and you see here, this is a closed surface. This is a closed surface. So if I want to find the total flux, if I want to find the total flux over that closed surface, that means the total flux over the closed surface, I have to integrate over that closed surface. Okay, now you see I have used this notation, different notation. Previously when I defined the flux, I didn't use this notation. It is because I am actually finding the flux through a surface. Now this is a closed surface, so I have to integrate over the closed surface. Okay, then d psi. So what we will be getting? So this will be equal to integral over the closed surface, and sorry, we got it as 1 by 4 pi, okay, Q divided by r square into magnitude of ds. So this you will get it as the total surface area, 1 by 4 pi r square into Q into integral of ds, means it is the surface area S. So this is the surface area of sphere. What is the surface area of the sphere? You know the surface area of the sphere is 4 pi r square. So this S will be equal to 4 pi into r square. So this 1 by 4 pi r square into Q into 4 pi r square, you see this will cancel, and finally you will get Q. So you will get the total flux over the closed surface as Q. That's why the unit of charge is Coulomb, and the unit of flux is also Coulomb. So you are getting the total flux will be equal to the total charge enclosed by the surface. Suppose you have 3 Coulomb, then what will be the total flux around it? Then the total flux psi will be is also equal to 3 coulombs. Okay, so this is the idea, and this is known as the Gauss's law. So Gauss's law states that the total flux through any enclosed surface is equal to the total charge enclosed by that surface. So I hope this part is clear to you. Okay, so we will see some more things related to this. Okay, because we will see what is the first Maxwell's equation. So you see here that the flux, okay, over that closed surface is nothing but the total charge enclosed by the surface, and this flux psi is given as integral d dot ds. This is what we have seen. And also the total charge enclosed by the surface. Suppose you have something like a metal sphere, something like this, and you consider the as a spherical region around that metal surface. And let us assume that the charge density of this inner sphere, that is a metal sphere, is the charge density of the metal sphere is rho v. Then what will be the total charge? The total charge will be equal to integral of rho v, that means rho v is the volume charge density, into dV over the volume. So I can get my Q as integral rho v into dV. Okay. So I can write my flux psi is equal to the closed integral d dot ds, and this will be equal to the total charge, and this will be equal to integral rho v dV. Okay. Now you know that by using the divergence theorem, by using the divergence theorem, okay, by using the divergence theorem, we know that I will take this term, this is the surface integral. So divergence theorem will connect the surface integral with the volume integral. So integral this term over the closed surface d dot ds will be equal to the volume integral of the divergence of the d, okay, dV. Now I will replace this same thing, I will replace this term here with this one. So this will be equal to the volume integral del dot d dV. Okay. So I got a new equation. You see, I got something very new. So I can equate these two. So I will write it down in the next step. So integral rho v dV, that means you integrate the volume charge density, then you will get, actually you are getting the charge. This will be equal to, you see this are equal, that's what the divergence theorem says. So this will be equal to integral, okay, the over volume, okay, del dot d dV, del dot d dV. So if you equate these two, you can see this is dV, this is dV, and this is volume integral, and this is also volume integral. Now I can equate these two. So that means this will be same, these two terminologies should be same. So del dot D, that means the divergence of the electric flux density is equal to the volume charge density, and this is one of the Maxwell's equation. This is one of the Maxwell's equations. Okay, this is the first equation of the Maxwell. So this is one of the Maxwell's equation. Now I can say that it is the, I will say in words, this is giving you the divergence of electric flux density, okay, and what is this? This is equal to the volume charge density. Okay, the divergence of the electric flux density will be equal to the volume charge density. So this is giving you, this is the Maxwell's equation. So I hope it is clear to you. Thank you.